All right, so welcome to the West Wing. We are looking at dynamic memory allocations. Essentially, we talked about the stack quite a bit, and we've seen how things are passed into functions, how we make use of the stack by moving things on and popping and pushing. But really, there's two main sort of ideas about memory. There's this concept of local memory that is local to individual functions, that has this idea of scope, where one function can't necessarily reference variables that another function defines and uses, and that you can define the same variable within different scopes because they exist on different stack frames. When we start talking about dynamic memory allocation, that is more of like a global scope, we end up allocating that memory on the heap. And the heap is something that's actually doled out by the kernel. So you say, hey, give me some memory. The memory manager will say, all right, I have this much memory available. I can't process your request, so let me ask the kernel for more memory. It'll then break and get some information like a buffer from the kernel, and then it'll manage all that information, that structure, and it'll say, all right, here's your buffer. So what ends up happening is there's some sort of magic that happens behind the scenes. So you might say, give me 32 bytes. I want 32 bytes of data. And what'll happen is the memory manager might go, here's 1K, just shut up and leave me alone for a while. And then you might sort of like realloc or copy more stuff into that. And then you might want to like slowly add more data to it over time. And then finally, you would have to go back to the memory manager and say, hey, listen, I need some more data. Can you please like help me out? I need more data. And it'll look at all the information that it's collected and say, yeah, I have a little bit more. Here's another K, or here's 512 bytes. And only at the point where it needs to go back and beg for more will it actually go back to the kernel and say, hey, give me more memory. So it's going to keep track of all these different pools. Now imagine you have to keep track of all of this memory. There's blocks of memory in between other blocks of memory that are being used. They're being freed, but memory isn't being squashed down and coalesced. There's this whole memory manager concept that handles all of this stuff. And the implementation of the memory manager is extremely important to understand how that structure works, how efficient it is, what really happens under the hood when you ask for a small amount of memory versus a large amount of memory. And all of these things really sort of boil down to this really naive concept where you just say, give me some memory, and then you just use it, and then you free it. All of the hard, really complex things of coalescing all of that data, keeping track of it, being a broker between you and the kernel is all magically handled by the memory manager, and it is amazing because you don't have to worry about it. But what we want to do is at least just introduce the concept of this heap and realize that everything that we want to do, we can't put on the stack. It turns out that when we compile an application, we need to provide type defs because we need to say this is an integer, and an integer is a 4-byte value in 32-bit land. And you need to say it's an unsigned integer or a signed integer so that it understands how to represent or encode that data, right? So all of this stuff is really important because there's a fixed amount of space that's available on the stack. And when you enter a function, it's going to subtract from the stack pointer to create, quote unquote, create space or create that stack frame that exists for that session or that particular function call. You can't just put an arbitrary amount because you'll end up blowing away the stack frame. So in order to overcome that, you end up doing this process where you allocate memory on the heap. Okay. I've talked enough. Let's go ahead and take a look at what the next challenge is. So in this case, what we're going to do is go to the West Wing. Type in the West Wing. And right away, without doing anything, it seems it's not asking me for any input. So it says, you enter the West Wing. It looks like a magically... the typo's still here. It looks like a magical toy assembly line. Boxes are materializing out of thin air and vanishing before you can read what's written on them. Poof, a box appears next to your head. Crush, the box collapsed on itself and vanished. Then we type any character and we're brought right back. We have no control over what's going on. I can't type something in and manipulate what happens or change the outcome of this particular wing. So this is interesting because it's the very first wing that I can't just type something in and change the course of execution. I actually have to figure out what's going on here and what it wants. So what we'll go ahead and do is go into the West Wing and try to understand this particular process here. So right away, one of the things that stands out at me, other than seeing this toybox.txt, is fopen. Fopen is trying to open a file. So it's trying to get some particular permissions on a file. It ends up trying to open toybox.txt, and then whether or not that particular open was successful, it'll either end up failing or coming over here and doing some stuff. What's really interesting is in this particular case, there is a collapse that happens and then a free, but we're freeing what? It turns out that malloc actually hasn't been called, so it's odd. We actually end up calling free on a null value. Let's see here. This particular value is set to 0. This is in here. So I just noticed a bug in the code. This free should not be here. But it turns out that it's actually okay to call free on a null pointer. Usually null pointers are bad things. You don't want to operate on null pointers. It turns out that it's okay to actually call free on a null pointer. Look up the documentation, and it ends up being okay. I've had this particular case where I've gone down this rabbit hole before and tried to see whether or not there's actually any negative side effects. That is completely useless and not needed, because it turns out the pointer that was like sort of declared, the variable that should hold a pointer to the malloc memory, ends up being freed when it's never actually set. It's only set after we do a read or we open a file. So this is completely unnecessary. It won't actually cause anything weird to happen, but we don't need it. So that's cool. I was able to find a bug in assembly and not in C. Awesome. So anyway, what we have here is this particular basic block comes down here, tries to open toybox.txt. First of all, I know we need to add that. And since there's no like other like path or anything, what I'm going to do is assume that it's looking in the current working directory, which is my desktop. So let me minimize this and we'll create this toybox.txt and see what happens. So let's go to here. I'll type in toybox.txt. It's there. It should see it and be happy. Let's type in 4. Poof, a box appears next to your head. Crush, the box collapsed and vanished on itself. All right, so not good. We had this hypothesis that if we just added this file so that this particular path can go this way instead of to the right, what we would do was end up like just getting further, and it seems like that didn't happen. But in reality, we can tell that we did some malloc of some size, and then we memsetted that to some value, and then we did an fread. Here we go. So we do a read on the file, and it turns out whether or not we get bytes back is a determination of whether or not we fail. So in this particular, it says crush, the box collapsed on itself. So it turns out this jump of equal to 3a here and 3a, if it reads 0 bytes, then it's going to fail. So fread will return the number of bytes that was read from that read operation. So we just basically need it to be something else. So let me collapse this, and I will type in bike, B-I-K-E. Let's save that, and then we'll run this again and see what happens. I forgot to save it. Apparently. No, it's there. All right, cool. So let's do it again, and it says, all right, what the fuck? Okay. So so it turns out what actually happens is I name this toybox.text, and it's actually toybox.text.text. So let's do this. I'll open up something here. ls. It is toybox.text.text. Oh, geez. So in my really tired stupor, what I've done is actually continued to go down this path without realizing it. So let's go ahead and fix that by renaming this. So now that is in fact the toybox.text, and we'll come here and type in 4, and now it says, poof, a box appears next to your head, wrap, 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 wrap. A perfectly wrapped present appears before you. You open it, revealing a key in the shape of a bike. Bike is what we typed into the actual file, so this is perfect. When I hit enter, we end up coming back here, and now we have 4 keys. Awesome. So really what we wanted to define or kind of talk about in this particular case is really introduce this concept of the heap. It doesn't really end up being a major portion of this because all we have to do is just understand that we can get past this point. So what's really interesting is that in certain cases, we may not know how much information is actually in this file. It turns out that we end up actually capping the amount of data that we actually read. So in this particular case, we set 32 as the malloc range. And then when we do fread, let's see here, this is put onto the stack at ESP. There's a malloc here. What we end up doing is limiting the amount of data that we read. fread has a value of how many bytes it'll actually read, and we set that to 32 or 20 hex here, and then end up reading that block size. So in this particular case, we could have done this on the stack, but we chose to do it on the heap. It turns out if we're asking for lots and lots of memory, and when I consider lots is probably more than like 1K, you definitely don't want to do it on the stack. As a matter of fact, some compilers will probably yell at you if you try to allocate a stack buffer of more than maybe 1 or 2K, which is actually quite large for that. And that's not a lot of data. So imagine if you're trying to read in an audio file or like a PCAP or something, they're going to be pretty large. And in order to process that, we need to get a larger contiguous memory region, and malloc is going to do that for us. So we've kind of seen the effects of what that actually looks like, and these frees, and we've even been able to spot a location where we free something that has never actually been malloced, and we're just freeing a null pointer. Turns out that's perfectly fine, and it doesn't matter if you end up doing that, but it's something that's completely useless to actually do. So this is the end of the 4th wing. There's one more wing that's secret, and we'll go into that in the next video. See you then.